What's up, everyone? Welcome back. Today we are yet again working on our neural network training framework. This is, part of a series of us trying to make a food tracker app. Where one of the things I want the food tracker to do is like keep track of the food in my fridge, right? So that, when I am stressed out, don't really know what I want to eat, I can like open the computer and say, what ingredients do I have and what things have I made before? Please tell me what to make. And so to do that, I think that, you could enter every ingredient that you have in your fridge and then keep track of it over time. But what would be nice is if I could just like, as I unload stuff from the grocery bags, just kind of like scan them with my phone and go beep, 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 beep. But to do that, we need a barcode scanner. And of course, a barcode scanner is not as simple as you would think. I think especially with a like camera sensor, right? Like the barcode scanners at the store, they already don't really work that great, but they have like a grid of like a mesh grid of these like lasers that they have like high control over, and like will create like super high contrast on the things that the bars are like meant for, right? We have like examples of the where the data of like the lines is becoming like pretty low resolution or like low frequency. There's cases where the bars themselves are actually like made of mirrors because the aluminum can, they just etched off the thing. And so then you've got like stuff like lighting to deal with and warping to deal with and like shadows where one side will actually be like, you'll have like sharp change in brightness that isn't a bar. You have like stuff like this where the bars are fairly occluded. So our answer to that is, instead of like trying hard, we will make a neural network that will maybe like isolate bars for us, maybe just predict the codes directly. Haven't quite decided that yet. And of course, if we're going to train a neural network, then it's unfair of us to use somebody else's neural network training framework, so we're making our own. And here is his current state. We have images of stripies that are being generated, as well as a red line that indicates their orientations, and we are trying to predict, with this blue line, what the orientation actually is. We've had some success on this thing. If we do fully connected linear layers, like your typical, every time you've seen neural networks on YouTube, you see like this picture, right? Where they draw these like lines where they kind of say like, you connect each input to each output, boom, 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 boom. Each of these lines has like, some like weight to it. And so these kind of like indicate like multiply adds, where you're multiplying each input by something. If we just make every single one of these inputs one of the pixels in our image, we can like predict something. That's like a pretty like inefficient way of doing this. A thing that people actually might do in practice, kind of like stage 2, I guess, of like image recognition networks, is you do this thing called like a convolutional neural network, where you take a box and like maybe like a 3x3 box, and you fill it with numbers. And that 3x3 box indicates like, for each pixel you look at, let me multiply and add each of the like surrounding pixels by the number in the box, and you can create all sorts of like effects with that thing. So if you look at like image kernel Wikipedia, we have some examples. So looking at this picture of this little guy, you can do like edge detection by saying like, look at me compared to my surroundings, like negative the guys around me, but positive me in the middle. You could do like horizontal or vertical line detection if you were to do like 3 negatives at the top, 3 positives at the bottom type shit. You can like sharpen or blur this thing. And the idea is that like, instead of learning, you learn like a bunch of these little boxes, right? And these boxes should produce features that you can like then run more boxes over and build up like high level concepts. We have proved to some extent that like we are seeing these boxes attempt to learn something, right? So let's see if we can find here. Here we go. So these are the image gradients for one of our 3x3 boxes. So every time we like showed an example, we go like, how wrong were you? And could you please like adjust yourself accordingly? And what we find is these numbers are like quite small. If we look at like kind of the how an image progresses through this network right now, let's see if we can kind of show this. So we start with like this picture, right? We feed this to the network, and the first thing he does is he like has 2 of these boxes, and the boxes that produce this like blue means negative, red means positive right now. So he produces basically like a negative and positive version of this image, which isn't very useful. And like we can probably find that here with these 2 kernels. So he's running like something that looks like this and something that looks like this over the thing and producing this. Then we're like, your typical neural network thing is to basically, instead of just like outputting what you did, you like say, was this thing like turn this into a yes or no. So like you might take your outputs and you might throw them through a function that looks kind of like this. This is called sigmoid, and this is what we're doing right now because it was like the first one that we did. It basically kind of lets you build up complex behavior bases off of like if things are on or off, kind of like how like neurons firing or whatever. And this has worked pretty well for us in linear layers, but in convolutions, what seems to be happening is if you look at the output of this thing, it all of a sudden just like squashes it, and you're like losing a lot of detail by doing this. And if we do this every layer, so here we have a couple more outputs, boom, then he gets squashed a little more. And by the time we get to like the linear layers, which like kind of look like this and take in, they kind of go, let me look at each pixel, boom, 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 and like feed that into one neuron here, and then like you have another neuron that goes boom, 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 kind of like you do on your typical neural networks. It seems like either there's not enough data in here for it to learn something meaningful, or the training is like so fucking slow that we can't like learn something meaningful with the like squished, like not very useful data we have, right? Because this is what these guys are seeing. Gross. And so what I want to look at today is trying to fix that. So we have a few things to try. One is that like if I look at like real convolutional neural networks, how much data do you have? Infinite data, because we generate it on the fly. My bet is on no activation on the convolutor. Yeah, that's one thing to look at for sure. So yeah, if you look at like normal neural networks, if I look at like the one we've been referencing a little bit is YOLO v1, because that's like one of the first ones we looked at. But we also looked at like maybe UNet as well. If you look at like the stack of shit that they do, let's see if can I find the fucking picture. Oh, is this not YOLO v1? Yeah, that's not helpful. I want YOLO v1 paper. You only look once. Here we go. So something that they will do, I thought that I saw it in here. Relu. Do I see Relu anywhere in this document, or are they just not doing activations at all? Maybe they're just not doing activations at all. Maybe in this one we saw Relus. Yeah, here we see them use Relus, not sigmoids, which is like basically like a different activation function. So if you're trying to say like, give me like for any set of inputs, turn them into something like a little bit more on-offy, sigmoid kind of looks like this. Relu will kind of look like this. So they kind of like preserve everything above 0, and anything below 0 they just clamp to 0. So this is like something that I want to try. No activations for convolutions also might make sense, right? I think that activation, do these guys just not use them? They might. Can we look at like YOLO v1 PyTorch or something? Just like I want to see models probably. YOLO v1. Oh, here they're using leaky Relus according to this code. So I have seen this, where leaky Relu is kind of like the same idea, but instead of just clamping to 0, they kind of go like, they might go like, this is 1-to-1, and then on the other side they kind of go like, ugh, so that there's still like some gradients over here. You need the activations, otherwise your network is essentially a linear map. Yeah, that was my understanding as well, but I think with convolutions, it gets like a little bit more complicated, because like you're kind of doing multiple passes that make like your receptive field larger, and might like, you're kind of like maybe turning into like a bigger kernel or something. Not really sure. But yeah, I agree. I have to think about it a little bit more. But I wouldn't be shocked if you could get away with on convolutional layers not doing that, right? Because you're still saying convolutions are still linear maps. Okay. Because like I could see an argument that's like, you do like a horizontal edge detection, and then you can like look at those, you can build another kernel on top of that. But I guess what you're saying is if you had a big enough kernel, then you could just do that directly, which is fair, I guess. Okay, so let's try adding support for Relu to our thing. Another thing that you see in these, also, I guess let's cover that as well, is you'll see people do like, they'll do like batch norms is something that I see as well as like, but I guess that's not in here. But I've seen batch norms as well, and then I also wouldn't be surprised if like maybe what we have now, like the architecture kind of works, but like we can't get the weights to move enough at the back section because all we're doing when we're like adjusting parameters is kind of like poking all gradients equally, where you could like add momentum to like certain weights, and maybe we could like get the kernels to train faster than the linear section and like speed up in that way somehow. But yeah, first thing I want to do is try Relu. Leaky or non-leaky Relu. And let's just see where that takes us. Okay, so the way that we have this stuff set up is everything is kind of going through OpenCL kernels. We have these like, at this point, we've kind of got this like layer interface where we kind of can just specify like a sequence of actions that we want to happen. So I guess here we add, next to sigmoid, we have Relu. And this turns into Relu layer. Okay, what does sigmoid layer look like? Let's just copy paste this and we'll kind of see where that takes us. So this is going to be Relu. He has no weights, true. Which means that all he has to do is run executor Relu. And then this guy is going to say, I am a Relu, sir. And I'm going to construct myself a Relu, and this is a Relu layer. Okay, easy. So now we can replace these with Relu, like this. And we can kind of see what happens. He's gonna not build, probably, because Relu doesn't exist. So we have tracing executor. This guy is the guy who, he builds up like a computation graph of everything that we've done. So like, in order to do training, we kind of like run a bunch of stuff, figure out how wrong we were, and then like walk the whole execution graph backwards and see what happens. So like every multiply we do, every add we do, every operation has to be like written down so that we can kind of backtrack it. And so that's kind of this guy's job. So one of the things that we might want to do here is we have Relu, and he happens on some node in the graph. Cool. Which means that here, like, we copy paste the sigmoid function and we call it Relu. He's probably got the same format. And he probably calls Relu here and he says, I am a Relu, sir. And so then he has to actually do some math. So in here, we need to do some math, I guess. So wherever our sigmoid function is, we copy paste this and say Relu. He creates a buffer that matches the input buffer size. For convolators, usually the max pooling source is non-linearity. Oh, interesting. Yeah, I can see that. 100 samples isn't enough per iteration, is nowhere near enough to learn anything. I mean, it's been effective for our linear layers. I think that, like, sure, we can bump it up, but no matter how much I do, it doesn't learn shit. And I kind of lowered it intentionally so that the variance would be higher, so that it would maybe, like, kick itself out of, like, getting stuck. Or I've seen that work in some ways. But sure, like, yeah, we can go higher. But yeah, it is 100 samples per iteration. Yeah, maybe. We'll see. Cause we can just like bump the learning rate up as much as we want, right? Like, there's nothing to. Yeah, I mean, we'll see. Okay, this guy's got to execute a Relu, which doesn't exist yet. Relu kernel. So here we need to like create something that runs on GPU. So we create a function here in OpenCL land that says, for each unit of work, please do something, right? So here our function is going to be like, he's going to take in, I guess, an input, an output, and number. So in, out, and then how many units of work there are. We say, hey, could I get my ID? So I am work unit 10 out of 10. Technically, we actually we queue more than we actually have in buffer size because you have to like you need to like queue in like multiples of the work group size or something, so you might have to queue too much. So we just do a little check here. If, you know, ID is greater than or equal to n, we get the fuck out of here, no work to do. Otherwise, we just take our output and assign it from our input. But we only do this if if inval is greater than 0, we return inval, else 0. And in this language, it's like this. Easy. So there's our relu. Return x greater than 0. No, no, right? That would be like true or false. You need to like pass through. What's this relu? It's basically a function that looks like this. Boop. So anything less than 0 gets mapped to 0. Anything positive gets mapped to whatever it was. No, you mean the gradient? Oh yeah, true. We'll get there. We'll get there. Okay, so here we need to, you know, compile this kernel for our GPU and extract it somehow. So this is relu program content, comes from relu CL, easy peasy. We need to stash that shit somewhere. Okay, and then here it's again sigmoid relu. Okay, cool. We also do need some gradients for backpropagation. So like, how does a change in say I am like, I have some value here, right? And I'm saying like, hey, this value affects my final answer by like how to say this? This affects my final answer by like some amount, right? So any change here is like results in a 0.4 change in my answer. How do we like propagate this change backwards, right? So we want to know how like we have, if we, when we came into this function, we were also this number. So it's like the same, right? But if we came in and we were like some number below 0, we were like over here somewhere on the line, this gets clamped to 0, and any change here doesn't result in any change in the output, right? The output of this thing will still be 0 no matter what. So I think that our gradient function is literally just like, hold on, relu CL. So I think we usually take in like downstream gradients, as in like this number here. How much does a change in our output affect the final output? Then we also take in our input. Yes. And our outputs, typically. And we say, if, we do the same thing here. If inval is greater than 0, we no longer return inval though, we return the downstream gradient. We kind of continue on with what the final answer was. But if we are less than or equal to 0, then probably if it's less than, it might be here, like, it might be less than or equal to 0, because technically if you bump 0 a little bit forwards, it will move. But whatever. So otherwise here, then we have no effect. Cool. The adjoint derivative is indeed just x is greater than 0. It drives me crazy that everyone in the MLO community thinks that gradients are somehow being what is being computed, but you have no idea what the tangent space and bilinear form of that gradient could. I don't know any of those words. But yeah, I agree with you. The gradient for, like, yeah, you're right. The gradient for this thing is just 1 if it's greater, 0 if it's less, because it's linear. But we're composing it with the downstream one. So I think that this is right. Pretty sure. Pretty sure. Okay. So here, when we're doing back propagation, we look at our execution graph, and at some point we see, hey, there was a fucking ReLU in there. And so we have to do something with that. So I assume it's going to look very similar to what we did on the sigmoid, where we say, this is our input. We call ReLU grad with downstream gradients in our inputs. What's going on here? Add a sign. So here, oh, sure. So we like add our thing to our gradients for the input were 0. We add the gradients that we calculated, and then we continue our back propagation. Easy. Easy. Which means here we should be able to be like, hit me with a ReLU grad. Bang, bang, boom. And he's just going to be like, ReLU grad kernel, and then downstream in red. Is that what we said when we made our kernel? Downstream in red. Yep. N. Cool. So it looks like we're kind of chilling. And then that might compile. That compiles, and it might work. It'd be cool if it did. Okay, so if we look at our layer outputs now. Okay, so this looks kind of like it's working, right? Here we're seeing that this whole thing is below 0, and when we apply the ReLU, this guy just stays the way he was. And then this guy who's like lots of blue, only like the positive parts make it through, right? And that's only happening sometimes. So that's kind of nice. We see some evidence that something is happening. And as we kind of go forwards now, we can kind of start to see, oh, this guy's doing some shit, who then again gets like ReLU'd here. We're losing a lot of data on this kernel down here again. Right, so this guy's all blue, which means that the ReLU kind of just like clamps that motherfucker out of here. And so what I'd like to see now is, that's a really good sign too, is we are now starting to see the blue line is actually moving, right? So all we did here was we replaced sigmoid with ReLU, and he is actually, like, the loss number here is going down, right? This used to get like clamped at 60, now we're going down to like 30. We can see him starting to learn something. And so maybe if we left this for long enough, it would start working. So that's kind of hype. That's kind of hype. I wonder if we can like try learning more now. So what if we're like, yo, we got like tons of room. Let's just do batches of like 1,000 instead of 100. Add LR slider. Yeah, right now it's like hard coded, which is annoying. I am kind of down. I agree. LR slider is like definitely worth it. Because like I've been like recompiling the over and over and over again, and you're right. Like it's just so easy to do this. Okay, where does this come from? GUI thread. Somewhere, we need to add some slider that is like a drag float of some form. Maybe this goes kind of at the top somewhere, and this is like learning rate. This guy goes, you know, pulls from somewhere, and we'll say that this guy is like, when it changes, does something. Gen LR update or something. Here we say, hey, you're going to ask for an LR update, which comes from a floating point number, and you need a function to make that thing. This also gives you the feeling of cooking just like a stove. Yeah, so true. So true. So he's like, LR update is the value that came in here, easy peasy. The GUI, when he asks for what happened this frame, we might go like, hey, somebody move the LR up, the learning rate thing. And here, we're like, first of all, let's update the learning rate. Is this value, but we need to clamp it, so let's like make sure it doesn't go below 0, at least. And here, I guess we have like a learning rate lives here now, or something. So this goes away. And so now this guy has to make it, maybe we call this default LR so that the training thread can start with it somehow. So when this thing changes, we must have like a message that we push over to the training thread, right? So somewhere, I guess here, after we change it, we probably go like comms GUI send train request, and this is going to be like update LR is the new learning rate, easy peasy, and now we have to add that to the things that we can do. Easy. Easy. Now on the training thread, we're going to like get that thing, right? So presumably this won't compile anymore. First of all, because he needs to have his variable LR here, which is var LR is default. He starts with the default. Yep. And then somewhere he's gonna get mad. Oh, I guess this is const for now, just so that it compiles. Here, he's like, yo, I got a new learning rate. Can we return update LR? Could you please, like, thread who's doing the work, could you please, sir, fucking update this shit? Cool. So now we need this, like, this action to get propagated. So it's like update LR like this. This is now union enum because sometimes he has data associated with him. And now the training thread's like, here we have like this. Now here we have update LR, and we go LR is equal to new LR. Easy. Easy. Technically, this is going to make it so that we don't process other messages from that. We might want this to like be something like this where he returns many actions or doesn't exit here. I'm gonna put a fix me here. Maybe don't like process as many requests as we can before returning, because like this only happens once per training loop. So if your training iteration is like your training time is like really slow, then a lot of learning rate updates could cause some problems, right? So I guess, yeah, I mean, we have to fix this. So the new thing that we're going to do here is this is going to be a struct, and this is going to be like each of this guy. This is going to be like this, right? So now what we do is here we have like return is a notify action like this. And if we see any of these things, we like assign, we go like ret shutdown is equal to true. And here we like immediately return because we don't need to do anything else. So shutdown is kind of a special case. Here we say like, we probably count how many times we toggle pause. So here we say pause count is 0. And here we say pause count plus equals 1 here. Okay. And if we have update learning rate, we say ret learn it like update LR is LR, easy. Is thing gonna switch like a pointer receiver for an honest function in Zig? It's like yeah, it's like the unpack union thing. Like similar to how like matches in Rust work. And then here we don't have anything to do on our return. Structured bindings, yeah, that sounds right. So here now we say ret pause count, or toggle pause is pause count %1. I guess we could just do this. you can do this again, where we go do wrapping add on a U1. And then toggle pause is bool. Can we do like, I guess it's like pause count is greater than 0, like this. And then return ret. Okay, so now these learning rate updates won't like slow down our like parameter receiving. And now here we just don't switch this thing. So we say like actions is this. And then we just do each of these. We can do them all at once even. Right, so here we do whatever we were doing for toggle pause before. If actions update learning rate with the new learning rate, we do this. Right, and if we have shutdown, we return. Easy. Okay, nice. And then we also have const lr here, and this is a variable now. So that might work. Might. Forgot to write try there. All right. So now what we should be able to see is if we look at the gradients here, and I just kind of like, oh yeah, okay, so I don't know what the fuck happened here. Okay, so the learning rate, we need to change the speed of this slider. That's fucked. This guy gotta move way slower. Okay, here we go. So if we look at the gradients now, if I like start turning the learning rate up, you can like see them grow. Right? I mean, yeah, if we crank this too high, obviously it's gonna break. So maybe we should like clamp it in some way, but maybe I should just not be a fucking idiot. Right? Sick. Sick. So now we can like inspect each layer output. Oh, hell yeah. Hell yeah. So this learning rate's probably too high. We should probably go back. We should really, this slider is still way too sensitive. I'm almost down for like another 10th as sensitive. Probably a good idea to clamp at 1 anyways. Yeah, surely we don't want to go that high. I agree with that. I agree with that. I agree with that. There we go. Oh, we actually nanned super early this time. I don't understand, partially. It could just exponent, not value. Yeah, true. That's probably not a crazy idea either. So, like, I don't, like, fully understand. I feel like training should be, like, deterministic. And it's, like, very much not. All of my random parameters are, like, seeded. But something is causing it to, like, sometimes I nan. So I'm concerned that, like, we're, like, initializing weights with, like, invalid parameters at some point. But whatever. Okay, so let's see if we feel like these guys are significantly moving now. Okay, so this is really good, right? We were seeing before that, like, our kernel weights were moving, like, incredibly slow relative to the linear layers, right? But now we're seeing these guys are moving, like, 0.01 almost, like, relatively quickly. And if we look at that compared to, like, the linear layer weight movement, do we feel the same? Right, so here's, like, a linear layer. The linear layer is actually moving less. So that's, like, that's pretty good, because, like, now the convolutions, which are the guys who are supposed to be, like, extracting meaningful data, are the ones that are, like, doing the relevant work. It should be deterministic on initial weighting. Yeah, I agree. So I think that we're probably somewhere accidentally looking at invalid or uninitialized memory. It's like the only explanation, because everything else is seeded. Yeah, look at that. Look at that. Okay, so now also what we should be able to do is we should be able to like reduce the amount of linear layers a lot, I think. I think we should almost be able to get away with like if I were to do this by hand, I think that I could do it with a couple convolutions, right? Find out the horizontal and vertical gradients of the whole image, and basically just normalize those values relative. Like if you sum the whole image and then normalize it, then you should have like the correct orientation of the bars. I think a hand wavy. So I'd be curious to see if we can kind of like get something that works okay with a smallish network. So let's just kind of see. Where's my train loop? Here. So maybe let's do something like, you know, a 5x5 kernel that creates maybe like 4 channels of outputs just in case like they initialize poorly. 3x3 is probably fine. Another 3x3 that goes like 4 down to like 2. We have a linear layer that takes that full thing and turns it into linear outputs. So like here we should be able to get away with like something relatively small here. And then even here it would be kind of interesting to use Relu's here as well. Maybe. Just gonna see what happens. Let's see what happens. Learning rate down a little bit. Oh yeah, look at that. These numbers are getting pretty fucking small, pretty fucking fast, dude. Look at that. We're in like the single fucking digits already. That's hype. So if we like, maybe we give it a little more time, we could even like eliminate even more. Go down to like 0.2. And while it's doing, oh, look at that. That blue line is tracking pretty close. Still a lot of volatility there. Yeah, I agree. But, you know, we've only been training for a few seconds. Yeah, this is working like very well. Look at that. We're getting down to like 3. Oh, baby. Learning rate even lower. Fuck it, you know? Let's get like, I'm curious to know what these like layers are producing. So we can kind of like look at that. So like this guy doesn't seem to be producing much value. I would think, oh, I guess we need to compare with what the training example is. Okay, so we have this image. Let's look at the layer output. Fuck. So this is, oh, I see. Okay, sure. So this guy's probably doing a lot of heavy lifting here. The rest of these guys, I don't really see anything that's like super interesting. Maybe one of these are like horizontal and vertical kernels. Who knows? Oh, that looks like a horizontal gradient here somewhere. Depends on how the network is using it. Yeah, I agree. Yeah, so maybe like we can't really infer much, but it is kind of fun to see what it's doing. So here he's going like creating these 4 guys. Then we go here. So here we're saying that half of these, basically like half our kernels here are useless, right? So we've gone, oh no, sorry. This is 4 to 2 outputs. So he's taking these 4 inputs and turning them into something. So as we flip through these, it would be cool to see some sort of like difference between horizontal and vertical, which I'm not really convinced I'm seeing, but maybe on the next output we do. Anyways, I don't really know. It's kind of cool though. We're seeing something. Something. And then eventually we head into these like linear layers, which are doing like some shit. Who fucking knows? But eventually we get down to here. Oopsies, I didn't want to change that. And for each image we get something different. Crazy. What fun. What fun. And so we can kind of see, at this point, we flip through images. Blue line's tracking okay. Not phenomenally, but not that bad either. If you want some sort of L1 regularizer, you'll see useless stuff actually go to 0 and die. That's cool. I would love to see that because eventually when we like export this stuff to run on CPU, I was thinking like I want to push weights to 0 so that we can prune those weights when we're doing on CPU on phone calculation. Is that what that means? L1 regularizer ML. What does that mean? Improve model accuracy by preventing overfitting, which happens blah blah blah. Help similar model perform better on new data. I don't really understand. This doesn't really like explain it. So this guy's doing like adds the absolute value of the magnitude of the coefficient as a penalty term to the loss function. Penalty can shrink coefficients to 0. Nice. It's cool that this is like a thing that exists because this is like an idea that I had. Not like the absolute value of the magnitude here, but I did have the idea of like trying to nudge weights to 0 to kill them. So it's cool that that is a thing that people do and works. That's pretty cool. Why does it help though? I don't understand why this would. Overfitting, which, oh, dude, what is this ad? Overfitting, which happens when a model learns the training data too well, including noise and outliers. So you're basically saying like, hey, don't fucking learn things that aren't like the most important things, I guess is kind of what this is saying. That's the L1 bit. You can regularize for any LP form. Interesting. Okay. So this went smoother than I thought it would. The like other things I wanted to try, I guess like a better optimizer could help us with like training convergence speed. And then the batch norm stuff I guess isn't really important yet. So probably like the next steps of things I want to do are like add strides to the kernels that we can like start getting into like smaller sets of gradients earlier, as we try to start stacking up onto like more difficult training tasks. But yeah, I think that like the next thing is probably, now that we've solved, we have a network that is a convolutional network that can solve this like uber trivial problem of figure out the direction of the bars. We're going to have to start working towards a network that can actually do some of like the barcode stuff we're thinking about, right? So the eventual, like probably masking bars is like the first thing that I want to try. And I need to think about that a little bit, like how I want to formulate that problem. So we're probably gonna need to work next on like improving data generation, improving, then like setting up a network that tries to actually predict something reasonable about barcodes. And then if that's too slow, then adding some sort of like better optimizer is probably done then. So I guess I don't really have a plan for today. So I think I'm just gonna call it now instead of bumbling around like an idiot. I'll think overnight, see what we'll do tomorrow. I'm sure there's something, I just have to figure out what that something is. But cool. Thanks for watching, guys. Feel like we stream most days. We aim for 12:30 Pacific time. Usually we try to go for longer than today. Lost 1, woo, yeah, it's pretty exciting. We usually aim for like 3 or 4 hours. Today was shorter because it went too smooth. I didn't have a backup plan, but that's okay. We're working on this neural network stuff, but there's a lot of other stuff in the backlog. If you want to check that out, there's a YouTube link in the Twitch description. Some stuff goes up there, probably like the majority, or the majority of like feature development goes up there. Some stuff does not. Stuff like cleanup, unit testing, reading, that type of stuff goes on Patreon or YouTube members or Twitch VODs. If you pay in the appropriate place, you get access to the rest. And you get some of the knowledge that you are helping the stream, the lifetime of the stream continue. So consider supporting, consider dropping a prime. Obviously no pressure. YouTube, peace out, and Twitch, let's find someone to raid.